So then we have Dmitry Vagner.
Hey, thank you very much for organizing and hosting this.
Great, yeah. So, and the title is Wiring Diagrams as Normal Forms for Computing in Symmetric Monoidal Categories. Please.
And everybody can see my screen?
Yes, we can see. We can see your screen.
Yeah, so this is joint work with Evan Patterson and David I. Spivak. So, trying to figure out where to put the zoom bar so it doesn't distract me. So, let's talk about symbolic expressions in an algebraic structure. So, formally, given an algebraic structure with generating operations, expressions in them are like abstract syntax trees. So let's consider a monoid, where the operations are a binary, which I'll label as dot, and nullary, which I'll label as 1. For instance, this messy looking thing with a bunch of parentheses. So typically in math, people almost never write out these parentheses because we know that the operation is associative. We know that we have unitality. So instead we just write a dot b dot c dot d dot e. That's simple as that. So even though at a very formal level, we have these parentheses, we tend to exclude them so that our syntax can encode our laws and hence allow for more visual reasoning. So alternatively, we can give sort of unbiased definitions. So by unbiased, what I mean is that a monoid is typically presented with a nullary unit operation and a binary multiplication operation. What if instead we defined an operation that just worked on any list of elements, so n area for all n, and returned how those elements combined into a single monoid element, i.e. a morphism from list m to m. So for each m list, a comma b comma c comma d comma e, you assign its single product in m. So this sort of world of unbiasedness has a lot of different formulations. There's many different categorical technologies used to describe them: Levier theories, props, monad and operad algebras, etc. In this work, we'll be focusing on operad algebras. So one advantage of unbiased definitions is that they sometimes can give us normal forms. So for instance, look at these two nasty monoid expressions with all this parenthesization. They're both equal, and one way we could deduce that they're both equal is we can reduce both of them to the simple ABCDE. So the normal forms allow us to reduce a test for equality to one of identity. So if you have two expressions and you could simplify them all the way down to their normal form, if those normal forms are the same, then those two expressions correspond to equal terms. So the goal of this talk will be to define an unbiased definition for morphisms in a strict symmetric monoidal category, and then use this definition to specify normal forms for computation in symmetric monoidal categories. So in a strict SMC, morphisms are generated by composition, and I'll be using the semicolon to mean diagrammatic order rather than circle, meaning the opposite order. Identities, tensors, units, which in the context of morphisms we use for the context of generating them, we use as identities of the tensors, identities of the units, and then betas, which are braidings or symmetries. So for example, if X is a morphism from X to X tensor Y, and G is a morphism from Y tensor Z to Z, we can write down morphisms like F tensor IDZ, then, or composed with IDX tensor G. And then these morphisms, just like in the monoid world, things were subject to associativity and unitality, we have things like the interchange law. So that's sort of the distributive law of how tensor and composition interact with each other. So if we tensor F and G and then compose with F prime tensor G prime, that's the same thing as doing F composed with F prime, tensor G composed with G prime. So ideally, just like in monoids, we went into the world of just lists as our sort of way to represent expressions in normal form. We would like something similar for morphisms in an SMC. So one idea is string diagrams. So the key notion is that fundamentally, morphisms in a symmetric monoidal category, or any monoidal category really, are best represented in two-dimensional form. So, and this starts out with Penrose diagrams and then was formalized by Joyal and Street. So for instance, we can express the morphism that we defined on the last slide as the following wiring diagram. And one, I think, perhaps this is a subjective view, but I think this is a much more clear depiction of what's going on. You have the F and then the G and sort of how they hook up with each other in terms of what information in terms of domain and codomain they're like attached with. And what's nice about string diagrams is that they notationally have baked in, just like our unparenthesized version of monoid expressions, things like the interchange law. So both these expressions are rendered as this square of morphisms, and this square is well defined. There's no ambiguities there. So, but one issue with string diagrams, at least in terms of how they're classically defined, is that they're topological. But we would like, for the purposes of computation, something very combinatorial. So here come wiring diagrams. So one of the main distinctions between string diagrams and wirograms is as follows. So in string diagrams, if you want to compose F and then G, you can compose them like so. But you can't really represent the composition operation itself, the thing that takes an F and G and gives you that composite. So wiring diagrams are meant precisely to do this. So note that they look quite similar. There's two differences. One is that in wiring diagrams, the inner boxes are left empty, and one should think of them as sort of slots for arguments that correspond to morphisms of the correct type. And furthermore, there's a circumscribing rectangle corresponding to the output type. So almost viewing these as like a Russian doll rather than the final composition. And what's cool about wiring diagrams is they can be used to define structures, like categorical structures, purely in terms of what kind of compositions they allow for. So the way in which we compose wiring diagrams is via nesting. So if you had this picture over here, this wiring diagram over here, and this wiring diagram over here, and you wanted to put this one inside of slot 1 over here, you would get this composition. So operads of wiring diagrams have been used to model trace monoidal categories, hypergraph categories, and even just regular old categories, which we'll look into now since it's the simplest and most fundamental example. And then in this work, our goal is going to be to model symmetric monoidal categories this way. So here's the wiring diagrams for categories. So given an object list T0 through Tn, so that's n plus 1 objects, the wiring diagram seq for sequential T looks like this. It's literally just n boxes chained together inside of a wiring diagram. And the goal is that this wiring diagram corresponds to the composition map, the n-ary composition map that you would get in regular categories. So recall, categories are defined typically in a biased way with a null-ary identity arrow and a binary composition operation. But associativity and unitality, just like in the monoid case, allow us to have an unbiased sense of just taking the composition of a chain of morphisms. And this is precisely what this wiring diagram codifies. There's two special cases, which I call unit and inert. So unit is a zero-ary wiring diagram. It has no boxes inside. There's just an outer box. And what it does is, note that if you have a zero-ary product, you just have a singleton set. It corresponds to a map from the singleton set to just Hom XX. Well, what's the only map of Hom XX that we can definitionally construct? It's the identity morphism. So the unit picks out the identity morphism. Now, inert corresponds to a unit in a more meta sense, in the sense that it is the unit on the Hom itself. So this just says that if you only have two objects, then the composition for that single arrow, that single Hom, is just do nothing to that Hom. Keep it as is. So send F to F. So it's inert because in the composition of wiring diagrams, this acts as the identity morphism there. So then where do all our laws go? So we replace our two laws, just like we replaced our two operations with wiring diagrams, we replace our two laws with a single coherence condition. And informally, we could just state it as ignore intermediary boxes. So if you're composing these wiring diagrams by nesting, it just says, oh, and sorry, this dash should be here. It just says that it doesn't matter what the intermediary boxes are, just ignore them. Whatever the final output is, that's all you care about. So associativity can then be encoded as the special case where you do this maneuver, i.e. we first compose the first two and then compose it with the third, or we first compose the second two and then compose it with the first. And unitality similarly, except exploiting this sort of unit which picks out the identity. So we can assemble this into an operad. So our objects are just going to be, so okay, first we'll choose a set tau, which will correspond to our type of objects. And we can define a thin typed operad as follows. And we're going to call it S sub t, S sub tau. So objects are just pairs in tau. Excuse me, this t should be a tau. And we call them boxes. So really you should think of this as a slot for an arrow. All you care about is specifying a domain, which is an element of tau, and a codomain, which is an element of tau. Then for each non-empty list of objects, T0 through Tn, we have an n-ary morphism, which is given by seek. And I said that this operad is thin, which means that HOMs are either empty or singletons. These are precisely the singletons. All other HOMs are empty. So what's special about thinness is that in a thin category, so in a regular category, a thin category is just a preorder, all diagrams commute. So this fact that all diagrams commutes gives coherence for free. So you can think of these associativity and unitality pictures as corresponding to various commutative diagrams in the operad. And this says that, well, they're all vacuously going to commute. So we get our coherence for free. So furthermore, we can even define a category in terms of an S-tau algebra. So, and what do I mean by an algebra? Well, an operad can be seen as a type of symmetric monoidal category if we view the operad as coming from an SMC where the multivariate, the morphisms with multiple inputs correspond to tensoring the inputs. So this would just be like a symmetric monoidal functor to the Cartesian category of sets. So given such an algebra, the objects of it, we can create a category H bar whose objects are tau. The HOMs correspond to where you send the objects in our operad. The classical composition binary corresponds to sequence on 3 objects, and the identity corresponds to where you take the unit. And then thinness implies the coherence and hence associativity and unitality. And note that there's a kind of level shift in perspective, because the arrows from our category are now, those verb-like things are now noun-like. What we care about is the compositions of those arrows as our new verb-like things. So objects become types, which is some higher level we're going to. HOMs become our objects. Composition operations become our arrows, and our laws become coherence. So we're now going to try to do this in the SMC world. And before doing so, we're going to need to take a brief detour. It'll at first maybe not make sense why, but we're going to be using the language of biproduct categories. So note that a biproduct category is a category whose coproduct and product correspond. And we usually use this O+ symbol for it. So what's special about biproduct categories is if you have a morphism from a direct sum of a bunch of things to a direct sum of a bunch of things, we can extract components on both sides by inclusions and projections to get exactly how a TI interacts with a VJ. And in so doing, we can literally extract an entire block matrix whose components correspond to how each pair in the domain and pair in the codomain interact in this morphism. And furthermore, we get the nice property that composition of morphisms is literally computed with matrix multiplication, the same matrix multiplication that you saw in linear algebra. And that one is indeed a special case of this picture because the category of vector spaces is a biproduct category. So why are we doing this? Well, one family of biproduct categories is given by spans. So if you have an extensive category C, so Any topos corresponds to an extensive category, so don't worry too much about that. The category of spans in it, so usually spans are a byproduct category, or a bicategory, but we're going to quotient out the one morphisms and only consider isomorphism classes of them. So we get that spans of C is a byproduct category. And in fact, the coproduct in C corresponds precisely to the byproduct in span C. So recall that a span is just sort of a span from one thing to another thing is a kind of, is an arrows, is a roof with arrows going both ways. Excuse me, there's a typo here. This A should be a TI and this Y should be a VJ. And here, and in this specific context of spans, how would you extract morphisms? How would you extract these components? Like here we extracted components by these inclusions and projections. Here what you do is, this is literally the inclusion, this is literally a projection essentially. And what you do is you take the limit of this diagram to get the specific way in which one component interacts with another. So from that, we can take a span and generate a matrix of subspans. In fully decomposed form, so if we're dealing with C being a set-like category with the notion of element, in fully decomposed form, we're going to treat entries of the matrix as just the sets. Why is that? Well, a span whose 2 feet are just singletons, the only data we care about is what is the set connecting those 2 singletons. So we'll sort of abuse notation there. Just like in linear algebra, a block matrix has each morphism, as each entry as a linear map, but we conceive of, as in a full matrix, fully decomposed matrix, each morphism as being a scalar, when secretly that scalar is a line-to-line linear map. So here's an example. So the way we're going to be thinking of spans is as sort of wirings. So here's the interpretation we propose. So if we have a span with roof S going from X to Y, we can interpret the terms of X and Y as left and right nodes respectively, and the terms of S as wires connecting them. So let's take a look at this RST to XYZ matrix. So this set C corresponds to the fact that T gets connected to X via wire C. A comma D corresponds to the fact that T gets connected to Z via both A comma D. And this B corresponds to the fact that R gets connected to Y via B. So we can depict this via this diagram as follows. So we have the RST on the right, the XYZ on the left, and a wire connecting them. 2 things to note. One, a graph in this sense is just a wiring from X to itself, where X is the set of nodes, and then the set of wires are just the edges. 2, given that interpretation, this matrix with set-like entries is essentially like an adjacency matrix, except rather than simply saying yes or no to whether or not 2 vertices are connected, we give the set of wires or edges that connect them. So this lets us sort of, we now have the tools we need to define what a wiring diagram for a symmetric monoidal category is, which we call an acyclic wiring diagram. So given a set tau of types, a box is a pair of tau typed finite sets. So those are just finite sets where each one is assigned a type. And then a wiring diagram is with inner boxes T1 through Tn, outer box V, is a span in the category of bijective, in the category of bijections of spans of tau type finite sets, where we're looking at so we call the negative the imports and the positive the exports. The imports of the outer box direct sum with the imports of the outer box, and the exports of the inner boxes are then connected via this wiring diagram to the imports of the inner boxes and the exports of the outer boxes, where this boldface T is just direct summing across all of the T sub i's, or T to the i's. And furthermore, we stipulate the progress condition. We write Ti as strictly less or strictly precedes Tj whenever there's a wire A for which the source lands in the box Ti and the target lands in the box Tj. And we want, for when you to write this, it yields a valid post set on the TI, not a preorder, a post set. So here's an example of how we stitch these wires together. So the inner boxes are the S, S prime, S double prime, and the outer box is T. The wires are A through Z, and here's sort of just the definition of the span. Now let's look at a non-example, the ones that have loops, which is what we're trying to forbid, because in a symmetric monoidal category, you have a certain acyclicity we want to preserve since we don't have any traces. In this, the wire A means that T is less than T prime, but the wire B means that T prime is less than T. And that's a contradiction. That's not a valid post set. So how do we compose wiring diagrams? So I'm just putting this picture back to remind people what this looks like. So if we have an outer wiring diagram phi and an inner wiring diagram psi that we want to stick into phi, here's how we can define this composite. We're going to use this matrix notation to work out cases. So I'm going to make a brief substitution with U, and U sort of means the outer box V and all the other boxes T that aren't the one we're substituting in. So it's kind of the rest. So this psi S plus S minus corresponds to wires of the box we're substituting in that aren't interacting with the outside world. They're fully internal. For instance, this wire from the red to the orange. In turn, the upper right-hand corner corresponds to either phi from U minus to U plus, which are precisely the phis that precisely the wires we already had in the external picture, e.g. like this wire from, 2 to the outside. And we're adding in our passing wires, which are the wires that go from a box Ti to Tj in the internal picture, e.g. this one, and then connect outward via these composings of the wiring diagrams to the outer box. And the two on the
Dmitry,
diagram.
do you think you could wrap up in a few minutes?
Yes, of course. Sorry about that. So in short, these wiring diagrams assemble into an operad via this notion of composition that we call W tau. With these wiring diagrams, we can define the standard symmetric monoidal category structure maps, the symmetries, sequential composition, parallel composition. You can show that interchange law works as you want, along with any other law. And we can combine this into a theorem that roughly says that if you start with an SMC, you can extract a W ob C algebra. If you start with a W tau algebra, we can construct an SMC. And then doing 1 followed by 2 yields an equivalent SMC. Finally, part of why this project was even inspired is via CATLab. So SMC wiring diagrams have already been implemented in Julia in the CATLab library, which our co-author Evan was the flagship developer on. So the CATLab library includes data structures for wiring diagrams and their compositions. The wiring diagrams have underlying data structure graphs, very similar to our spans. And furthermore, the wiring diagram composition algorithm proceeds via case analysis that corresponds one-to-one to the matrix entries of our definition of composition. And if you want to learn more about CATLab, tune in to Keynote Talk in session 2 on Wednesday to hear Evan and collaborators discussing it. So thank you very much.
Yeah, thank you. Very nice. Yeah, I guess we have a few minutes for questions. So just speak up. Well, so then maybe I'll start. Just out of curiosity, have you thought about the case of braided monoidal categories at all? Is there hope to find a corresponding description in terms of an operator wiring diagrams, or would it just be too complicated?
It's something I've thought about, but it would either A, involve thinking of things as an embedding, which would get very topological, or B, using a kind of not theoretic framework that's very like combinatorial and looking at involving Reidemeister moves. So I think it would be pretty complicated. I don't think it's not doable. It's definitely interesting, but the proofs would be very messy without some better technology to describe them.
Okay, thanks. Yeah. More questions?
I have a question. I'm not sure whether this is better for this talk or for maybe if Evan's talking about his implementation, but why is, what's the use of spans of bijections? So in the book that David and I wrote, we sort of developed a similar formalism for called, which we term port graphs, which are very, very similar. But instead of sort of giving each wire a name using a span, we just have this sort of bijection from inputs to outputs. Does that play a big role in the later theorems that you developed on this?
So the main reason for using spans of bijections rather than bijections, and you're right that spans of bijections are really just bijections. We can forget about the wires. But if we use the span framework, we have the ambient byproduct category of spans of regular functions. And with that ambient byproduct category, you can use the categorical matrix calculus to do bidirectional case analysis in the sense of case analysis on both input and output wires to correspond to entries of the matrix. So I think that this could be defined in the regular just bijection framework, but the definition would be A, asymmetric, and B, a little messier, I think.
Okay, but it sounds like Evan's implementation. I think you said in the last slide it uses graphs rather than spans. Does that mean it's easier in that case to not use these sort of representations, and why is that?
I'll let Evan answer that. I'm not sure exactly what the design choices
were. So in the implementation, it basically allows the spans to be non-bijective, to have non-bijective legs. And that's convenient because then you can represent supplies of monoids or comonoids on your monoidal category in basically an unbiased way as well, by allowing splitting at ports. That's effectively what that does. And so that generality is used in the implementation. It's actually quite convenient. So.
Okay, cool. Thanks.
And the definition here can be rapidly expanded by taking out the bijection condition to correspond.
Thanks. Also, great talk. Thanks.
Thank you very much.
Yeah, we're a little over time, so maybe let's move any further discussion to Zulip. And yeah, thanks to all speakers again. And yeah, I think this wraps the day up.